Hello, everyone. Welcome to Facility Compliance Think Tank presented by Soleran. My name is Lance Wolf, and I'll be your moderator for today's webinar. And this is the last webinar in our three-part series related to building strategies. Today's subject is reducing cooling costs during the summer season. Soleran's happy to announce that we're now an ASHRAE continuing education credit provider. So after today's webinar, you're going to receive an email with an ASHRAE certificate for attending. But remember, you must stay on the webinar for the duration to receive your credit. This webinar has two purposes. First, we want to discuss the best practices in the areas of facilities, life safety, emergency preparedness, and other compliance-related topics. And second, this series of webinars was created to help healthcare professionals network together and share ideas. We want to see this network grow. A little bit of background on me. Again, my name is Lance Wolf, and I'm the Director of Life Safety Compliance here at Soleran. I'm a former life safety code surveyor for Joint Commission, and I have over 17 years experience in hospitals at the director, senior director level. And during that time, I oversaw engineering, emergency preparedness, safety, biomed, security, and environmental services. Here's a little bit about today's speaker lineup. First, we have John Schmidt. John Schmidt is a healthcare sales engineer at Trane, and he's been a healthcare sales engineer with Trane for the past 18 years. He started his career as a controls technician and then a controls sales engineer with Honeywell. And he received his bachelor's degree in biomedical sciences from Western Michigan University in 1984, and is also skilled as a master electrician. After John, we have Craig Elliott, and Craig is a healthcare vertical market leader at Trane. Craig's been in the healthcare industry for over 10 years, and currently he received his bachelor's degree in electrical engineering from Auburn University in 2001. He has over 20 years of professional experience in the HVAC industry, and he served as the Montgomery Branch Chair and Alabama Chapter State Board member for the U.S. Green Building Council. After Craig, we have Clayton Smith. Clayton Smith is a Senior Director at Children's Health System of Texas. Clayton Smith has 15 years of experience in healthcare facilities management, as well as 10 years in construction management and design. He currently is a Senior Director of Engineering for Children's Health System in Dallas, Texas, where he oversees 3 campuses totaling 5 million square feet of hospital, clinical, and business occupancies. Clayton earned his bachelor's degree in construction management from Missouri State University and his MBA from Webster University. So we'd like to appreciate and take time with all of our speakers taking the time out of their day to provide us with their knowledge on this topic, and I'm sure it's going to be informative for everyone here. A little bit of housekeeping items is each panelist has about 15 minutes utilizing PowerPoint slides. So take screenshots. We want to make sure that you feel free to use this webinar for a reference for future education. After our speakers are presented, we're going to have about 10 minutes for a live Q&A session. So please use the Q&A button at the bottom of your screen to ask your questions. Don't use the chat, specifically use the Q&A button. And if your toolbar disappears, just scroll your mouse over it and it will reappear. Now on the last slide of this presentation, we're going to have FCTT's web address on it, so you can utilize the site to help you network in the future. We want to see this network grow. Well, let's go ahead and get started on the webinar. John and Craig, are you there?
Hi, Lance. Yes.
Great. Well, we'll have at it, and we're looking forward to hearing what you have to say.
Awesome. Thank you, Lance, and Soleran for inviting John and I to be a part of this panel. Thanks, Jill, for keeping us on track here. We hope this will provide all those joining us in this webinar with some valuable insight into chiller system design and optimizing the plant for a more efficient operation. This presentation examines high-performance chilled water systems from the initial design to possible retrofits, control of other related items in the system, to redundancy. Typically, we would spend a couple of hours discussing these topics, as chilled water systems is definitely something we love to talk about. But today we will try to give you the highlights, and if you're interested in more information, feel free to reach out to John and I, and we will be glad to tell you the absolute best components for a high-performance chilled water plant. Today, though, our topics for discussion will cover chiller system design. We'll look at both variable primary as well as primary, secondary systems, optimizing the entire plant to include cooling towers and pumps. We'll touch on reliability and future planning, planning not only for future expansion, but also for the what if in the event of a catastrophic failure, as we are talking about mechanical equipment. We'll talk about how the rest of the building matters as well, like coils and valves, all the components that make up the entire system. And lastly, controls that make it a system. The building automation system ties it all together and should be used as your energy management tool, as well as a maintenance tool. Next slide, please. ASHRAE industry guidance has changed over the years. Many of us may still use a rule of thumb of 10-degree delta T with a 45 or 42-degree leaving water temperature, depending on your climate. Today, we see the more efficient plants operating at a higher delta T. On the chilled water side, the ASHRAE Green Guide now recommends a 12 to 20-degree delta T, again, depending on your climate. All of the advanced energy design guides that include chilled water systems recommend chilled water temperature differences significantly higher than the older methods. For the condenser side, the ASHRAE Green Guide and advanced energy design guides recommend a 12 to 18-degree delta T. And finally, the ASHRAE Learning Institute course on chilled water systems recommends beginning with a 25-degree chilled water delta T and 15-degree condenser water. Clearly, the industry recommends that systems be designed with significantly higher delta Ts and lower flow rates than in the past, but we will address designing a system to get the most BTUs out of your plant with the least amount of energy and cost. Next slide, please. One of the newer design systems is the variable primary flow system. The pumps are dedicated to the chillers, and the advantages are that you have only one set of pumps. The variable primary looks a lot simpler, and it saves on pumps and piping up front, so you could save about 4 to 8% on first cost. Likewise, you could save about 3 to 8% on your annual energy cost and about 3 to 5% on your life cycle cost. The variable primary flow system is designed to operate with variable flow through the chiller evaporators. For control stability and chiller reliability, the flow rates through the chillers and the rate of flow change must be kept within allowable ranges. Consult your equipment manufacturer should you need those allowable ranges, and they'll be glad to assist. Therefore, if we think about a control of a variable primary flow system, it must include a method to determine the system load, to ensure that flow rates through the chillers are within the allowable minimum and maximum limits. Modulation of a control valve in the bypass pipe is commonly used to ensure minimum flow rates through the chillers. Control the rate at which the system flow rate changes to ensure that it does not change more rapidly than the chillers can adapt. This is especially critical when turning on additional chillers. Adequate time must be spent designing the control sequence and commissioning the system after installation to ensure that proper operation of a variable primary flow system. It looks simple enough, but takes a good business partner that understands chiller plants to operate it properly. Next slide, please. Conceptually, a variable primary flow system is simpler to get right. The bypass valve is just below the chillers. And again, sizing that pipe and valve are critical to the operation of the plant. The valve in the bypass line only opens when the system flow rate nears the minimum flow rate of the chiller. So the bypass pipe and valve only need to be sized for the largest minimum flow rate. Usually that's the largest chiller's minimum flow rate, but depending on chiller selections, the largest minimum flow rate could be for a smaller chiller in the plant. It should be smaller than the pipe going into the largest chiller. If you're having issues with your plant or maybe experiencing what is referred to as a low delta T syndrome, and you know where your bypass line is located, you may look into the sizing of that pipe and valve. So confirm, confirm all the minimum flow rates. Next slide, please. So let's touch on primary secondary systems. Since the 1970s, variable flow requirements were satisfied using primary secondary systems. There's a primary pump for each chiller and secondary pumps that pump chilled water out to the building load. So it pumps in 2 loops. It also has a bypass line you see here just below the chillers. Depending on how much flow you need out to the building load, or the more 42 or 45 degree water that gets pulled into that loop, the excess is pulled through the bypass so that you are not wasting any energy. This is about 3 to 5% less efficient than a properly controlled variable primary system, and it uses more pumps. This is the old standby configuration, and sometimes you might have the thought of, if it's not broke, don't fix it. If you have it and it works great, it's easier to control. We might consider going to the variable primary configuration if you're designing a new plant. Next slide, please. In a primary secondary system, an easy way to determine if the bypass is sized correctly is to compare its size with the pipe going into the largest chiller, as mentioned before. Many chiller plants are tight with minimal space, and usually the hardest task is finding the bypass line, many times due to the fact of inadequate room in the chiller plant, tight spaces, which sometimes could be a challenge to find, kind of like where in the chiller plant is Waldo. You'll see here it's between the supply manifold and the return manifold. In this case, the bypass is 10 inches. The chillers here are identical and all have 10-inch lines, so these pipes were selected well. Again, it's worth repeating that it is critical to make sure the bypass line is sized correctly. Next slide, please. There are a lot of constant flow systems installed in every geographic location. We refer to this as low-hanging fruit for retrofit. Follow the steps shown here to convert from a constant flow system to a variable primary flow. This works well in single chiller applications because of its simplicity. It also works very well in retrofit applications where a chiller is being replaced and the owner is interested in operational savings. Only some of the 3-way valves need to be changed to 2-way valves, with remaining valves acting as the bypass. A speed drive can be added to the pump, and you have a retrofit variable primary flow system that should be simple to operate. It also works for design of simple new single chiller systems. The drawback is that there will always be more water being pumped than necessary, so pumping power will be a bit higher. If the minimum flow rate is low, the additional pumping power will be minimal. Next slide, please. So we need to make sure that we keep our attention and focus on the fact that the building owner pays for the system energy. You'll do your customers a great disservice if you allow anyone to convince them to just look at the chiller or a single component. Many owners have complicated systems in their building and use submeters on system components to provide data that tells them how their system is operating and maybe where to focus their time and effort to be in a continuous commissioning mode. However, always remember that the utility meter is on the building, and it's the building or the system that counts. Next, I'll turn it over to John. John, take it away.
Thanks, Craig. That was a good overview of the chiller plant and primarily the chillers. This slide kind of depicts how much each component of the chilled water system, at least in the chiller plant or around the chiller plant, how much energy it takes up. We have to look at all of them, as Craig mentioned. We have the chiller itself, which is the bulk of it. Although chillers with VFDs and the inlet vanes that we've had for years are getting about as efficient as we can. And there's the other components that are left with the tower water pumps, the building load actually, and condenser water pumps and fans to squeeze that little bit of extra energy out of your chiller plant. The bottom part of that graph talks about a good kW per ton plant. You can't get through a trained presentation without talking about kW per ton. So that's really the wire to water efficiency that we speak about. A good water-cooled chilled water plant, or excellent actually, is running in the 0.6, 0.7 kW per ton range. That includes all the pumps, the tower fans, the chiller itself. A good one is 0.7, 0.8, 0.9 is not even bad when you consider an air-cooled system runs about 1.7 or 8 kW per ton. So if we're not hitting that 0.7 kW per ton for the entire plant, that's all the pumps, tower fans, chiller itself, we know there's room for improvement. So we're going to look elsewhere, whether it's controls or design or whatever the case may be. So you might be metering your plant, and if you are, those are good benchmarks to gauge your efficiency with. Next slide, please. So we'll look at the cooling towers, okay? Colder is not always better because as the cooling tower water changes, it can actually make the chiller less efficient. There's more lift or less lift on the chiller. So a lot of companies have chiller optimization programs. We have one ourselves that utilizes wet bulb, dry bulb, and goes through some pretty complicated algorithms. And in this example, we have a 65-degree wet bulb temperature, and the plant's running at 60% load. Well, you might think colder's better, so let's drive that tower down to 72 if we can get it. But the reality is, by looking at both chiller and tower efficiency and optimizing how much fan energy we were using versus how much chiller and pump energy we're using, the sweet spot in this particular case is around 76, 77 degrees of condenser water temperature. So again, colder is not always better, and this changes, but there are programs out there and control systems that can automate that for you. So that helps on the tower optimization. Next slide. Estimated savings from that, it varies depending on your climate, but you see in a more humid climate like Miami, you can get 8.5% savings. A drier climate like Las Vegas, it may be down in the 2 or 3 range. And of course, somewhere in the middle is Chicago with 5.4% savings. So that's still significant when you look at a chiller plant, probably taking up 30% of a typical load these days of possibly of your entire building, because of lighting used to be a significant portion, but it's with the advent of LEDs, HVAC and chiller plants is becoming more and more of a spot to save energy. Next slide. We wanted to hit on some redundancy items. Most everyone likes to have a redundant chiller. I come from Michigan, so most hospitals do. If not, they really want to. I would imagine down south, it's almost a requirement because your plants are running 365 days a year. We get about a 3 or 4 month breather there. But you also want to look at the pumps. You may want a swing pump, and that way your pumps are also redundant. So if you only had one pump per chiller, obviously even if the chillers are running and one of those pumps goes down, you're still going to be short on flow. So it's good to plan for another pump as a redundant pump, as well as the redundant chillers. Next slide. Speaking again to redundancy again, a little blip on the air-cooled chillers. Again, I'm from Michigan, so we typically drain our chillers right after the first holiday in November. That is the opening day of white-tailed deer hunting. So we do that after all the techs get back from deer hunting and before Thanksgiving. That's not to say we don't get a 60-degree day in the wintertime. And if you don't have a air-cooled chiller that you can just fire up for your ORs or your other critical areas, it can take 6-8 hours to get that tower filled back up and run your critical areas on those warmer days. So it's a good idea to consider that. It's also helpful if the main plant goes down, for those of you in the south, to have that redundancy on your critical areas, especially your ORs. Next slide, please. Another piece of redundancy is contingency cooling. Basically what that is extending your pipes, both electrical and chilled water and even condenser water, to a location that makes it a little bit easier to bring in a rental chiller should you need it, or even a permanent chiller. They end up being permanent oftentimes, at least for an entire summer. But in the event of a catastrophe to the chilled water plant, or 1 or 2 chillers go down, you can connect a rental chiller to that system within 4 or 5 hours. And you can usually get a rental chiller within a day. Next slide. Finally, along the lines of redundancy, is if you're planning on building a new plant, put in an extra set of pipes. This allows you, the blue pipe and the green pipe above that empty pad there are examples of where we could tie in for that rental chiller should that be needed. And when you're building this new plant, it's going to be millions of dollars. So to add another 1,000 square feet and a little bit of extra piping for future, in the case that the hospital load grows, which most of them do, and also for that contingency cooling in the event of a major catastrophe. Next slide. So we bring this up again. It's a similar slide as Craig spoke to, but the meter is what's costing you to run that chiller plant. So we just want to emphasize again, there's more to the efficiency of the plant than the plant itself. So we're going to look at outside the chiller plant in a few areas within the hospital or buildings supported by that chiller plant itself. Next slide. So you can get help from the rest of the building through your cooling coil performance. You can have lower flow with the lower chilled water and increase the energy that way. Heating coils are often fairly old in a lot of hospitals, depending on where you're working right now, but those can get fouled up and they can be the source of pressure drop that's requiring you to run your 100 or 200 horsepower pumps in the main plant at full speed, rather than being able to slow those down, which is a substantial amount of energy. Next slide, please. So this is kind of a picture of that, an example of the air handling units and the coil that might be bad, or piping was undersized, or an area grew and required more chilled water. The graph at the right is an analytic that we run on a lot of our plants, that the bold red line is really the average of every chilled water valve in the whole hospital, okay? So you can see there's a blue line, and it looks like a maroon line that's going above that solid red line. So this kind of pinpoints, all right, these are the air handlers, coils or valves, or possibly some piping that is keeping us from slowing down the pump. We're having to pump all that pump energy just to satisfy a couple of odd air handlers that are driving that pump to run at full speed. Next slide, please. Some more help from the rest of the building are pressure independent control valves, or PIC-V valves as we call them. They come in a couple of styles. There's the mechanical and also the electronic PI valves. The electronic PI valves have an actual flow sensor in them oftentimes, and a supply and a return temperature. More flow does not necessarily mean you're going to get more chilled water out of that coil. There's a limit to that. And they're usually sized a little bit larger. So if you're having some troubles, you can oftentimes increase that flow, but there's a point of no return. So you can actually control to flow rather than temperature, and also be looking at the delta T of each coil. That also can pinpoint areas that might be of concern. Next slide. So, the lesson we've learned, many of us, I'm sure, have also learned out there that without controls, it's not a system. A lot of this information needs to be centralized. It doesn't matter whose system it is. If you have a chiller plant controls, I'd advise you to use somebody that knows chiller plants. That kind of goes by geography. Different manufacturers or vendors are better at chiller plants than others, depending on the area. But you want to, regardless, you might have 2 or 3 systems out there, but BACnet these days is a protocol that will allow you to poll all those chilled water valves, for instance, and determine how fast that pump should go, and whether or not you have a couple of bad coils out there that could be, again, driving that chilled water pump to run at full speed. A rule of thumb is you can get 3/4 of the flow with half the energy, half the horsepower of the pump. That just follows the pump curve. So if we can slow that flow down just by 1/4 or 25%, we're going to save half of the energy of that usually very large pump or group of pumps. Next slide, please. So in conclusion, we've kind of stressed the importance of a high performance chiller plant, and touched on the guidelines that ASHRAE has been changing, increasing delta T rates, compared variable primary flow for new systems, and primary secondary is still a good way to go. We want to make sure that you're sizing those bypasses correctly, or if it's an older plant, make sure it is sized properly, because you can get big savings by just correcting a small piece of the piping in the chiller plant. Tower optimization and pump pressure optimization are other components of the entire chilled water system that can help increase the efficiency of your building and your cooling needs. Prepare for your future and redundancy and potential catastrophes, and protect your operating room. That may cost some money because you're using an air cooled, but that's bringing in a lot of money. So we don't want that area or other critical areas to go down. And then don't forget your coils and your valves, because they can have a serious effect on the energy in your plant. Finally, of course, controls make it a whole system, because you're tying all this data together. And the more information we have about our building, the more efficient things can run. I believe we have another slide in case we had more time, but no, that's how are we doing, Jill?
Well, John, yeah, thank you. I think we're doing good on time. I appreciate the info that it was a great point about the OR, especially with having a separate system, because as you well know, there's many facilities out there right now that don't have that option. And so that's an excellent point for a future, especially if anybody's in future building design right now. Well,
yes.
Now we're going to go ahead and move on to Clayton, and Clayton is going to talk to us about chiller operations and maximizing efficiency within the facilities. So Clayton, are you there?
I am. Thanks, Lance.
Great, Clayton. Well, go ahead, take it away.
All right. Next slide, please. So a lot of what I'm going to talk about is almost very similar to what John and Craig talked about but from an owner and operator's perspective. Everything in our world from a chiller plant is driven by the delta T, and we want to make sure that we audit that delta T and we stay on top of it regularly. If you get a reduced delta T, we kind of go through a checklist of things we should do to go find the culprit. First, inspecting our cooling coils. Most of our cooling coils are not spring chickens. They're pretty old and they've been out there for a while. Amazing the efficiency you can gain in a system just by replacing cooling coils or giving them a really good cleaning to make sure you can maximize flow through those coils. The other thing we do, or it gets overlooked sometimes, is verifying the filter loading. Right? If our filters are loaded too much, we're going to push our system harder and ultimately reduce efficiencies. Validate the chill water supply temperature. This goes to something I preach, feels like daily at Children's Health, is that we're only as good as our sensors, and our sensors are only good when they're calibrated. And the smarter our building automation systems get, the more sensors we have, and the more we rely on them to be accurate. And I focus a lot of attention on training plant operators to have a sensor on the shelf, be ready to show up with that sensor and test it first. That usually, when we get into these situations, we'll break down a whole system trying to figure out what the problem is, and it's a bad sensor. So keep those sensors calibrated, keep them tight, trust the information you have because you've verified and validated your sensors. Inspecting control valve modulation. How often do we see an issue where we're not cooling a space appropriately or even overcooling a space and find out that the control valve is not operating at its full range, right? It's it's operating too much, so it's not actually throttling down the flow like it should. So we're overcooling or we're driving more demand on the chill water plant than is actually necessary. Or the other side, we have a hot problem, and we're just not that modulating valve isn't doing what it's supposed to. And finally, reviewing the differential pressure set point on the pump DP set point. This goes back to your sensors. Everything lives on our sensors. We spend money to install the systems. We spend money to commission the systems. We spend money to do tab on these systems. And then so often we just walk away from them and just trust that they're going to work forever without spending the time to go back in and calibrate and manage our sensors. Next slide, please. Chiller and pump staging. We talk a lot about running multiple chillers and pumps in part load as opposed to, maxing out load on a single piece of equipment. Just optimizing our equipment by running them in that sweet spot in the power curve, right? And understanding where that lives, for each individual piece of equipment. Another thing we struggle with sometimes is plant operators, they have this need for big equipment to run all the way out, right? And I want my big equipment to run. And when my energy person comes in, they want to run at maximum efficiency. And plant operators tend to, dismiss that the benefits of efficiency. An example of that is, you think of plant operators, they all want big 1-ton 4-wheel drive pickups, right? And but there's a place out there for a Toyota Prius, right? And a more efficient vehicle. And the plant operators, they want to do everything with the big truck, and sometimes you got to work on showing them and selling on what's the benefit of efficiency, and make it a goal for them, make it exciting for them to wring every ounce of efficiency, every BTU, every KW, every dollar we can get to make and really celebrate what these guys are doing to make the plant run not just harder, better, faster, but most efficient. Make that the target. Next slide, please. Another major issue we have from our chiller plant optimization is cooling tower water, right? We see makeup water volume increases and and we just kind of throw water in. There's so much water being used in our cooling towers. And when we see that volume increase happen, we want to go down through a checklist as well. First, evaluate your cycles of concentration, making sure your chemistry is right, making sure that we have good chemistry. We're managing not just the cycles of concentration and the chemistry of the water, but also if you do have deduct meters on that makeup water, that you're evaluating that meter as well. I just had an issue today where our municipality, one of our hospitals, basically eliminated all of our sewer credits for our makeup water meters because the meters were wrong and we weren't validating and managing those meters. So, it hit us in the pocketbook. Next, check in basins for leaks. I don't think I've ever been anywhere where I don't see cooling tower basin leaks. It's just one of those things. It's somewhat of a corrosive environment. There's just a lot of water happening. I spent all of my career in the South and Florida and Texas. That has a lot to do with it as well, because we don't get an opportunity to turn those things off. So, some time spent working on your chiller, your basins, making sure that you don't have any leaks and you're really taking care of your equipment. Verifying operations of sensors and floats. Going back to calibrate your sensors. Stay on top of your sensors. Make sure that we are using the right amount of water. Is it your basin float? Is it the flow sensor? Is it, what are those things? And really kind of back into that on that soapbox of calibrate and verify your sensors. And then last, review your check valve operations, making sure we're not losing water back into the system. Next slide, please. Finally, just some simple general maintenance items that I feel like we all know, but we need to make sure we continue to reinforce them. One, a clean tube's a happy tube, right? If your chiller's operating, it's got clean tubes, it's gonna run like a top. They get nasty and fouled, and your efficiency just drops. Second, verify your refrigerant charge. How much more compressor energy is being used because we have the wrong amount of refrigerant, either too much or too little. So verify making sure that refrigerant is charged appropriately. Analyzing compressor oil, perform a chemical analysis on the oil to provide details about the moisture content. High moisture levels indicate a purge problem or could indicate a purge problem. And finally, purge non-condensables. Those non-condensables can reduce chiller efficiency by almost 5%. And when you're talking about the amount of energy and the amount of resources we put into that chill water plant, 5% is a lot. And we're trying to, like I said, set that goal high. Let those plant operators be a part of your optimization journey and your efficiency journey, and reward them and prop them up whenever they are squeezing every ounce of efficiency out of that system. Okay. Back to you, Lance.
Great, thank you, Clayton, and thanks again for talking about, especially with running 24/7. You're right. You come across many different aspects that other hospitals don't have to deal with due to their geographical location. So now we're going to move to a surveyor's perspective and talk a little bit about when you're having your survey done. And I've had questions that have been posed to me on, what do surveyors really look at when they're going through plants and with the chillers, specifically. So we're going to emphasize a little bit more about that. So next slide, please. So a question that was posed to me one time when I was surveying is, do surveyors even look at the chillers in the plant during the discussion that we were having? And absolutely. Even though they walk through very quickly, your surveyors do survey of the plant and they evaluate the life safety components. They're looking around for additional open wiring, the common things that you'll see life safety wise. But they're also looking at the general condition of the plant, which also includes your chillers. So a suggestion that I have is when you're in your plants, it's kind of like the same statement that you'll use up on the floors when you're trying to look at, are the floors open, are they wide, is if it looks cluttered, the feeling is it's going to be cluttered. So walk around your plants and evaluate that on that perspective, on how they look. Do you have boxes around all over the place? Do you have open boxes over the place that are torn open because they've been sitting there so long and just parts hanging out? So these are all things that your surveyors are going to look at when they're walking through the plant. And that's going to kind of give them an indication of what they're going to find. With that, make sure that you have that looking in a manner that it looks not cluttered, it's very organized, and that's going to keep your surveyor from starting to dig a little bit further and start getting back into those back areas of your plant. They walk in, everything looks good, don't see any real life safety issues, there's not wiring hanging from the ceilings or J boxes, then they're just going to keep doing it, and they're going to walk through pretty quickly, but they're still looking for things. So specifically with the chillers is what they're doing is they're visually inspecting them to determine possible maintenance issues. They're not going to climb into it and really dig deep into it because they're basically doing just a quick overview of it. But some of the areas that they're going to be checking is one, they're checking the inspection of the water inlets and outlets for leaks. And that can be done very quickly as you're walking by. And a lot of times you don't even realize your surveyor is even looking at it. They might be looking straight ahead, but for me, I was still looking off to the side. I was looking around, like I just tell people when I'm doing mock surveys, and one of my suggestions is always make sure your head's on a swivel. So you're constantly looking around. And that's exactly what your surveyor is doing when they're going through their plant, is you might be walking forwards, but their head's moving around and they're going through and they're mentally checking off these areas and these specific components that they're looking for. So, they're looking for the water inlets, outlets, make sure there's no active leaks. If there are active leaks, they're going to stop and talk to you about it. And they're going to talk to you about the maintenance on it and what specifically is occurring. Next, they're going to look for your compressor unit. They're going to check that to make sure there's, leaks or any type of obvious signs of negligence. Do you have any oil leaking? Do you have anything? Is the compressor even working? Is the guard off the compressor? That's one of the things that that was common when I would go through, and there'd be a guard on the compressor, and that guard was pulled off. And that comes back to the OSHA 1910 reference in regards to guard safety. And so there were a lot of findings just in that area there, because that guard, obviously, it took time to take that guard off to be able to get in the compressor to work on it. And so your vendor would come in and they worked around it so much that guard was, they felt it was more of a hindrance than a safety measure for them. So they took it off. So these are all things that, when you're looking at your chillers, just kind of take it back from a perspective of not specifically what you would do, how you work on it, but what would a surveyor, kind of change that hat a little bit when you're coming in and you're walking around your chiller unit. And then another area that they look at is your electrical contacts. Are they going to be checked for safety? And are they looking at, and specifically what I would be looking at is not only are they connected? Do they look like they're being managed? But also I would also look at the coiling to see if they were pulled, if you'd been pulled on it and I had exposed wires. So that's another area that we get to where, we get so busy in our daily work where we sit there and we forget to look at that coiling and see if it's been pulled back and we have those exposed wires. So these are all little fine tuning that suggestions that I'll give to you, that I'm giving you to help you when you're walking around through your plant. And next slide, please. So another question that I get, and it was pretty common, was, okay, if there is a finding in the plant, what specifically is it? And it comes under EC 020505 EP6. And what that is the hospital tests and maintains the following non-high risk utility system components on the inventory. This specifically would be your chiller would be in this area. Now there is another nuance to this. If you're in an area like Clayton was talking about, like in the South, you're actually going to consider this a high risk utility system component on your inventory. And when you're doing your annual assessment, that's actually going to be rated higher than everybody else. But typically where the chiller is identified on the non-high risk utility system components. And so so make sure that when you're doing your assessment, that you're taking that into perspective based upon your geographical area. So anybody in the South, anybody in Arizona, that's going to be higher, and you might consider it a higher risk utility system component just based upon your geographical area and what type of weather you're getting all the time. Also, one thing that your survey is going to check is they're going to look for your completion dates, the results and the activities are documented. And if they feel that there's something going on or there's some type of negligence going on with the piece of equipment, they're not just going to go back to your past PM. They're going to start digging deeper. They're going to say either, give me a year of that. Some surveyors will say, give me a year and a half of it or 2 years of it, based upon what your manufacturer's recommendations are in regards to punching the tubes, your annual maintenance that's occurring. So they might go back 2 years as well, or to 3 years. It depends on what condition your piece of equipment is in and what specifically they found. So some suggestions, as like I said, is this finding is directly related to your maintenance program, because there's nothing specifically in environment care or life safety that identifies your chiller system. So that's another common question that I got is when we're walking through, people ask, hey, there's nothing specifically, like they talk about generators, you talk about ATS switches, those are specifically identified in EC and LS standards, but the rest of the plant isn't. And so that's where that question came from, is where else does this finding come from? And that's specifically what it is 2505 EP6 or 2505 EP5. Second is the specific finding is going to be then cross-referenced to the PM program, as I talked about earlier. So I'm going to go back, I'm going to follow that, I'm going to look at your PM program, and then I'm also going to ask for your manufacturer's recommendations and cross-reference that as well, to make sure that you're following your manufacturer's recommendations. Now, if you're not, if you're on an AEM program, then I'm going to ask you for a specific inventory list of your AEM program. And then I'm getting to the point where I'm cross-referencing now your chiller to your AEM program, and then that it's identified on there what the risk rating is. But you're going to want to be able to speak to it if you are using an AEM program for your chiller. And that's going to be the key, is you're going to want to be able to back up the information and close that loop of why you decided to go against manufacturer's recommendations. Also, discrepancies, they're going to be looked for, how to identify the lack of maintenance is occurring. So I would get to the question as well, is that I would start following back to say, why is this occurring, and start digging down to, is this a staff issue? Is this a manufacturer's recommendations issue? Is this an issue that is going to, is this an issue that you're even aware of? And there were a couple times where on surveys that the facilities director that was with me wasn't even aware of, that the PM maintenance wasn't occurring correctly based upon a staff issue. So these are where I always suggest to have, an audit program, a check and balance program within your PM program, within your system, within your EC tours, is that you're also checking those, because so many times we take those areas for granted. Next slide, please. Well, and that's all I have for today in regards to that specifically. My part is very short. So now we've covered a lot of information, and we're gonna open up for some Q&A questions, and we already have some in the queue I can see on the screen already. So we'll go ahead and move right to that. So the first question is, and this is gonna be actually for John or for Craig. So I'm just let which one feel that you're be able to answer this the most. Is the question is, what do you feel is the most important aspect to focus on while planning for an expansion with your current chiller system? And I know, John, you already talked about this a little bit as well.
Yeah, well, I think first and foremost is choosing the right team. You've got a number of different skill sets that you need to properly develop that chilled water plant. So, get with a good consulting engineer that works well with you. Subject matter experts, be those internal or external. And yes, vendors are subject matter experts. You have a pump expert, a chiller expert, controls expert. So, don't be shy on getting everybody's input, and stay involved in that design. Again, redundancy is important. A few thousand extra square feet on a multi-million-dollar chiller plant is again, money well spent for contingency and potential failures that you would run into down the road.
Okay, great. All right, so let's see our next one that we have down there. And then actually, this is another question for both you and John, or Craig and John as well. And the question is, are there any disadvantages, everybody, is focusing towards lead, as well, when you're building a plant and, especially a facility. And so that's a huge focus of going green. The question is, are there any disadvantages to focusing on designing a lead style chiller system, specifically in a hot climate or for a large system, larger facility, larger building?
Sure. Thank you, Lance. I'll take that one. From my experience, typically chilled water systems as designed meet lead in many cases. Sometimes we can overcomplicate chilled water system design. Lead design systems are great, and we all have a responsibility or should be designing energy efficient systems with sustainability in mind in an effort to reduce our carbon footprint. Sometimes higher costs can be a driving factor, and we must keep in mind the ability of an owner's in-house facility staff and their ability to operate the complex systems. I have seen complex systems, high efficient systems designed and installed on numerous occasions and be out of tolerance within a few months from set point or airflow changes and overrides. And all of a sudden that system is not operating as it was designed and intended. Specific to healthcare, it's critical that the system operate continuously as close to design as possible for compliance purposes. And ultimately, we know that it would affect patient satisfaction.
Yeah, exactly. Yeah, that's excellent points there. So we'll move on to the next question here. We've got a lot of questions, and keep in mind, everybody, and I'll touch on this as well, is we've got a lot of questions in the queue. If we don't get to your questions today, we will follow up with you. One of our panel experts today will follow up with you to help you with the questions that we don't get answered today. So this next one here, I think, Clayton, this would probably be this for you. And the question is do you do training in-house for new staff on your chiller systems, or do you require the new staff to have prior knowledge on the systems before hiring them?
That's a great question, Lance. It really depends on where the technician is. If we have an opening for a plant operator, we are expecting them to come with some plant operation skills, and either a specificity in boiler operation or generator operation or chiller operation. Now, we also are in the process of establishing a job description based training program for all of our technicians. And what that allows our guys to do is, one, level set on where they are. And so we know, and they know, where do you stand right now? And then as a maintenance technician may want to move up into a plant operator role, what do you need to know to do that? And is that, based on the job description, what type of training do you need? We're happy to provide that. We are all about growing people in-house as opposed to always looking outside. And then even so much that our organization offers tuition reimbursement that we can use to help support our staff as they try to grow themselves. So a lot of, kind of works both ways.
Okay, great. Okay, now we're going to move on to another question we got here. And this is going to be for you, John and Craig. And the question is, what do you prefer in regards to chemical dosing systems? Do you prefer chemical dosing systems and chemical-free systems for cooling towers?
I'll take that one. It's been my experience in the past that we would prefer chemical treatment processes. Not that chemical-free treatment it doesn't work, but we've seen the chemical type treatment systems work much better. And like Clayton mentioned earlier in the presentation, a clean tube is a happy tube. We've seen it work for years, and then back to the statement of if it ain't broke, don't fix it. Just my thoughts there.
Okay, great. And I think we got room for just one more question here. And unfortunately, John and Craig, I think that I'm picking on you with these as well. But the question is so it's in regards to the condenser water set point reset on the outdoor air temperature. They're asking, how effective is that?
I can try to address that one. On condenser water, we don't do a lot of that. Again, that's coming more from my area, my geography in the northern climate. We do look at chilled water reset being very effective. If I can change the question around a little bit, because there's rebates we're getting, I want to say $30 a ton for chilled water reset. Again, that may not apply down south, but and we look at quite a few things: the outside air temperature and humidity or enthalpy, and also look at chilled water return temperature. Condenser water, we don't, well, we do that with the tower fans, I guess, to control the temperature by looking at wet bulb and dry bulb both.
Okay, great. So, well, unfortunately, we do have more questions in the queue, but we're not going to have time for that today. So that's going to be the end of today's topic. And so, but first I want to thank John, Craig, Clayton for your time today. This was all great information that we can be benefited, that we all benefited from. And that was very obvious by the questions that we got as well. And so we really do appreciate your time today. So a little bit of reminders is one is you're going to receive an email with the link to the webinar to review in the future. And again, we want to encourage you to share this information with colleagues and get them involved in our future webinars. You know, we keep reiterating, we want to see this network grow, as well as our panel experts today. They're all involved with this as well, and they want to see it grow as well. So we also just want to remind you, we have a fall series starting in September. So look for more info in the coming months. And also go to Soleran.com hashtag think tank to check it out or watch for other webinar recordings for ASHRAE CECs. So, you know, if you weren't able to see our webinars in the past, go ahead and go back and review them, and then we'll be able to get you those CECs in the future. In closing, we want to encourage you to use Facility Compliance Think Tank Q&A and the group on LinkedIn to get any additional questions answered by our industry experts. And we want to remind you that this is, you know, an area to interact with other professionals in the field, and our panel experts also are going to be included within this group as well. So we'll be able to expand this into other geographical areas to be able to help you as needed. And keep in mind, all of our members consist of directors and facility compliance leaders all over the country. Well, this is going to conclude today's webinar. Soleran, Train, and our speakers would like to thank you for joining us. And we want to express a heartfelt thank you from all of us to all the healthcare professionals all over the nation who's been working tirelessly around the clock to keep us all safe. It's very appreciative, and we're reminded of it on a daily basis. And we want to give a big thank you from all of us. Well, we look forward to seeing you in the fall and next time. And thank you for your time today. Have a great day.